It was one of the first versions, and he showed it to me, and I was mesmerized. And I took it in, he sent it on to me. I compiled it and tried my own, and it ran, and I got a better simply for it. It was K, something like that, K shorts, and I was just, whoa. And I wish I'd written down the date, because little did I know what world I stepped into very early. So this I tried to apply to many of the analyses, and well, I'm going to maybe skip a few things here and there, but let's start with Atlas. And well, I'm not going to introduce the Atlas detector, fantastic place. Here is the very famous Higgs to gamma gamma peak. And the background is essentially all from real gammas. So better PID is not going to help anything. It's the width here, which is what you can try. And also for all the other Higgs channels, which for example, the case to the Z there, the Z has a width, but the Higgs doesn't. So if you can do it better, well, then you're popular. And CMS has a slightly better electromagnetic calorimeter. So we wanted to go at that. And the idea we had was to say, how can we perhaps use the calorimeter as an image, or as images? And we started with electrons, because electrons, there we can check if we're doing better, because we have the Z to EE, and if this gets more narrow, then. So this was one of the first, after doing a lot of PID, which machine learning is very good, this is what we tried. And it's also where I first came across attention. It's a while ago. So Atlas does it by having some input variables from the calorimeter tracking and so on. And well, what do you then have from the cells? Well, you have the energy, but you actually also have the time of the cell. And this means that if something comes out of time, you can sort it out. Unfortunately, the calorimeter doesn't have the same resolution in each layer, so you have to do upsampling for it to have the same resolution in order to use it. So this we did. Oh, this is and now the last thing we had was, apart from the electron track that goes out to the cluster, you also have a lot of other tracks, also from pileup, that you want to take into account. So now you have extra tracks, you have the variables that was already used, you have images with energy, and you have images with time. How do you combine those best? And this is a drawing by me and a student of mine, who said, well, let's try. And because these were images, we simply merged them here and use this as a gate. So a learnable time limit. And then we upscale it, and now we have the other things. And well, the tracks we put together first neural network, but then which is the best? We found that roughly this was the best. And here is a convolutional neural network. The thing is, why don't we just put it all into the top? Well, we tried that. That's what that shows. But it turns out that you can actually do better, because the calorimeter, the filters in the CNN that you run across, some of them are great at the barrel of the detector, some are great at the end cap, some are great in the crack, some are great when it radiates off a photon. And normally in the CNN, you just smack them all together in one go. So the question is, can you do better than that? And that's actually what something called film is. And this is, you want to give attention to the filter, which in this present situation is good. So we took the scalars and said, from this we calculate beta and gamma, which is a linear modulation of the weight we give to different filters in different cases. Right? Who should have the attention? And well, this turned out to be the best way to do it. So all this we optimized in simulated data. And then you try it, and in Atlas, well, here's the truth energy, and here's the reconstructed energy, and you want this to be as narrow as possible. You could see that it was 1, so that was nice. It's better to see it in 1D. So if you take the predicted divided by the truth, you want a sharper peak than 1, and you could clearly see an improvement. The improvement was of the order 22%. And this is enough that Atlas's calorimeter becomes as good as CMS's crystal calorimeter, which they paid a fortune for. So that's nice.
Before it was blind.
Before it's very cool. Now, one of the other things we wanted to see was, can we, those 22%, they were obtained using the truth. Could we do it without using the truth? And the answer is, you take the Z peak, and then you fit it with a bright paper, and then fold it with the resolution function, which could be Gaussian, but we actually used the crystal ball function, and that's it. Use the Gaussian resolution. And here's what you have before, and here's what you have after. When you put it in, we could measure it to be 23%. So we actually convinced ourselves that we, with the Z, we could measure it. Ta-da! Now we tried data. Okay? And it's unfortunately not a fun story, but in the end it is. Let's try it. 9%. It's better.
It's still 10%.
It's better, but right. And what the word here is that if you introduce a method, and I think this is one of the things you really have to focus on when you try to apply machine learning to data. If you do something that makes simulated and real data different, then you're walking into a lot of problems and so obviously. So we were, then you have to apply it to data and then apply it to Monte Carlo and smear that afterwards, or But well, what are the differences? Well, the difference is that you can actually train in real data with an assumption, two assumptions. If you find a Z where you then say, I trust that it will have the Z mass, and exactly the Z mass, which is an approximation, because that's a natural. And also, for measuring the energy of one electron, let's assume that's perfectly measured. That's another assumption. I can calculate what the energy of the other electron is and use that as a limit. The great thing is it has an uncertainty, but at least it's not biased in any way. So this we try. And then you get 6%. So it's even worse than if you trained it in the Monte Carlo. So there are so many things that the Monte Carlo has in strength of that relationship that you can't just ignore the Monte Carlo. And then came the idea, something we call hybrid training. Imagine that you train simultaneously in both the data and the Monte Carlo. Then the Monte Carlo is the strong pillar by which you learn the general relationship, complicated, million-dimensional relationship, and then the data will add the small differences, but not have to control a million parameters in order to get the best result. And and then, what does that look like? Well, you make the loss function simply a loss function with the Monte Carlo or a loss function with the data. We call it hybrid training. And it occurred to me that most of what we do in Atlas is that we train things in Monte Carlo and then we measure in data with control channels how good or bad this works and make corrections. But if you have a control channel by which you can do this, then you can almost always do this instantly. And now the hope was, well, maybe we could get 6, 9, and maybe we could get, the 2 in quadrature or something like that. First we tested, does it still work in Monte Carlo? It does. And then to the data. And you get 18%. So that's more than even adding the 2 linearly. So the sum is more than the parts, the overall is more than the sum of the parts. And this method, I think, in many sciences which rely on simulated data as well, can use this. I know particle physics is one of the leading ones with simulation, but and then here's a piece of advice, because what unfortunately happened in the period by which we developed this was that Atlas decided to not continue having the cells available for electrons and photons. It's like the blanket being, pulled away from you. So unfortunately, we could go as well as the CMS calorimeter, but no. And the other thing I liked about it, and that was taking the tracks into account, is that when you go up in pilot, the resolution in the current method, increases. Then it doesn't start 0, 0, but our method, advanced a lot more flat, especially for run 4, right? Around here. So I'm not done with the idea of doing this, just not with the calorimeter cells, but with at least the tracks leading to it, and training it, and hybrid training it around the electron, around the Z2. Yeah, please.
Question. How's the ratio between statistics-wise between Monte Carlo and Vega?
Yeah.
This works for. I guess it is being kind of easy to implement for electrons because you have a lot of C to E events, but for channels that are less prominent.
And I would immediately say less prominence or not the same momentum range or energy range you want. Electrons, for example, you have Z to mu gamma. The gamma is always 10 to 20 GeV. And if you could make it work around 60 GeV, that would be a lot more popular. For that, there's a smart method that I like beating gamma people for. They say a photon looks like an electron, except it goes deeper. Which means if you take the electrons and reweigh them to be photons, then you can use electrons, also in real data. This reweighing, and they did that, but what they did was reweighing one variable by the other. This means the correlations don't transfer. And this is what is the largest systematic right now. And behind these slides, there's a mail to eGamma, because with machine learning, you can reweigh in many dimensions in one go and have the correlations come with you. The algorithm is called GB. It's really, if you ever run into this, just remember GB. It's super good. So these are the possible next steps in this. Yeah. And then for physics, I work on this decay, because this is one of those that are still not discovered, but is probably going to be discovered in one field. So Atlas has great beat, 2 sigma, and CMS has 2 sigma, and together you could argue for 3 sigma. There's a paper with that, but of course, one of those we want to measure and see ourselves. So, and what is the background here? Well, again, it's a bit like the gamma, but only half. Half are just a light Z and a light photon, but it's just not confused. Whereas fake photons is also a part of it. So here I would love to do better photon PLE and maybe better energy, because you also get Z2E and a photon. That would be 3 things you can optimize on getting sharp. But what is not in the background here is wrong Z's, right? They don't even take that into account in the previous run 2 analysis. And this means that when you select the Z's, you should open up the box. As long as you get Z's in, you should open up the box. And this is what we're trying. So we are training an algorithm to say, here's a score of whether a pair of leptons is a Z or not. And the danger is that if you hand it all sorts of variables, even if you don't give it PT, eta, and phi, it will learn from the others that correlate with PT, eta, and phi. It will learn about the mass. And it will choose background if it's a little signal-like and is around 90, which means you're going to sculpt a peak. How do you get around that? Well, what we do is we say, we don't hand it all the variables and then say a Z. No, we train an algorithm to know, is this an electron? And you PID, 1 score. Is it isolated? 1 score. Same for the other one. And then what's the distance between the 2 and the vertex? Maybe the pi. Then now it knows nothing about the mass. We check that it's super flat in mass. And we're also happy to see that data in Monte Carlo correspondence is actually quite recent. And what you can do is you can have, here is what Atlas gets, and black is 100% efficiency, and well, black is if you don't make any cuts, and red is with the same background. But in fact, I'm for just opening the box. And this is after a pre-selection, which only keeps about 75 to 80%. So there are more Z's out there if you don't cut too hard. In the long run, in Atlas, I think in the same way as we have B-jets that are identified and so on, I actually think we should have Z's at least. You know, point back to the 2 electrons and give it a score, a mass, and an uncertainty of an X. This way, a lot of analysis will become a lot easier. Let's do this once and for all. And regarding systematics, people said, but systematics, you're going to have a problem because you don't know how, when you select the data with your machine learning algorithm, you're not going to know the efficiency. And just, if you have in simulation and in data, the Atlas numbers, along with the scale factor, the Atlas provides, then you know, the same Monte Carlo you select with the machine learning, and you know, like that number. And over here, you just from the fit of the peak say, well, I got 8% more for the same data. Then you just take that number and add 8% to it. The systematic is tiny, right? It might add another percent to it, but right now the statistics is plus minus 40%. So it's gonna drown. Yeah, so that's as far as I am in Atlas, and we work with a large Chinese consortium of groups on this, and they just want to publish now. So all of these things are things that take time to get approval, and so on. But the aim is for the end of run 3 to have the paper. Yeah. And I'm going to switch to IceCube. I sit next to a guy called Jason, and he is on IceCube. And we weren't always on IceCube, but he joined 8 years ago. And it's fun to be in a collaboration like Atlas because the expertise on methods, especially with machine learning, is just fantastic. And there's a lot of people. IceCube is 350 people, mainly astroparticle physicists, and they also have a detector, which, as you'll see in a moment, is not exactly so great for machine learning because it's very irregular. And for that reason, it was really fun to arrive, and I am not a member of the IceCube collaboration yet, but I'm accepted to work with them. But we've been part of making a small revolution in moving on to machine learning algorithms. It was an experiment that was really called ripe. You know, it was ready. There was lots of data, lots of Monte Carlo, lots of understanding, just no, and the algorithms that they were using for reconstruction and so on were likelihood, and some of them were 8-dimensional likelihoods that it took Multinest 40 seconds, sorry, but still a long time, per event to reconstruct. 40 seconds, yeah, but we use a lot of time in Atlas as well. We also have a lot of resources.
Yeah, we have to run tracking.
That takes, but not 40 seconds. And the problem is that they have to select events, you know, to get rid of backgrounds because they have as much background as we have in Atlas, before they could reconstruct what they were looking for. And that's just costly, efficiency, and time, and so on. And people said, Troels, if you can get it to run, even if it's not as good, but it's fast, then it's also good. Yeah. So we've been working on that, and I don't know how many of you know the IceCube experiment. It's Bohr, and it consists of 86 strings with 60 detectors on each, like pearls on a string, with domes that look down on people. And in retrospect, putting it in a hexagon was not so smart because then neurons can sleep in the corridors. And it's also nice to actually be able to look up. All these things burn, but it's still cubic kilometer, billion tons of ice that below the dust layer around here is so clear that you can see 300 meters. Right? Imagine going into the ocean and seeing 300 meters. If you see 20 or 30, you say, oh, it's super clear. Unfortunately, the scattering is bigger. So comparing seawater and the absorption is very small, but the scattering is. This is what it looks like when you put things in. Don't go in there.
Now, why the hole?
The holes, the detectors are like a large basketball. So 5 centimeters more than a basketball. The holes are of course bigger, but actually what's hard, it's not drilled, it's melted. It's only the top where there's the first 50 meters where there's no wall. Then it's melted, and this thing is hard to control because if it stays, it gets stuck, it gets wider and so on. Here's the detector, and there's a deep core which is more dense because then you go down in energy to where you measure oscillations. So IceCube is measuring oscillations between the second and the third family. They're competing with T2K, but T2K is just running out of statistics. They don't have that many. They have 30,000 neutrinos. We have 600,000. So now, for us, it's about understanding this tonight, but it's going to be the world measurement. IceCube is going to be for quite a while. And at the same time, it's a telescope. Breaking a 10,000-year-old monopoly that photons have had in looking at the universe. Finally, and I think 2017 is a fantastic year because it was the first year where IceCube got a neutrino, 270 TeV neutrino, pointed back, and astronomers said, yes, we see a blazer flaring up. And at the same year, we got a gravitational wave to which astronomers could look up and see a kilonova. 2017 is the year of revolution for multi-messenger astronomy. Slowly starting, but what do you then want to do? It's also a cosmic alert, because strangely enough, neutrinos arrive before the light, not because it's faster, but because it's emitted earlier. Light has to sort of make it to the front, whatever it's involved in, which has to be big in order to get to these energies. But neutrinos escape immediately. So it's a cosmic alert. And astronomers don't watch the entire sky, right? They watch 1/1000th of the sky for 1/10000000th of watching in some period, and then some other. This is 4 pi 24/7. I mean, IceCube is up 99% of the time. And so you can imagine, here's the problem. Sometimes you get 20 pulses, and sometimes you get 20,000 pulses here. And it's hexagonal, and it has layers of dust and all sorts of things. And how do you apply machine learning to that, right? You have 2 problems. A, it's irregular, so you can't use a CNN. Yes, people did it, but man, it was hard. You have to take this and turn it, move the detector parts and cut off the corners and put zeros there, and then. But a guy called Niels did it. I'm very impressed. See the model to say this took time, and he said yes, it took time. So it's irregular, and also it's tough because you don't have a fixed amount of pulses, right? It really varies. It's not like sometimes 20, sometimes 20. No, sometimes 20, sometimes 20,000.
For the same kind of event, or because events are widely different?
Mostly because they span 6 orders of magnitude in energy, right? And in Atlas, this doesn't happen. That's 3 orders of magnitude, right? You have a TeV and you have a GeV. And that's sort of the scale. But here you have a GeV, a TeV, and a PeV. So yeah, so that's why. With one former student, we discussed this, and then graph neural network came about. And it was 2018, and the first implementations, PyTorch came with PyTorch Geometric in 2020, and he got an ERC grant, and we started. But he lives on a far island in Denmark, Bornholm, which is way off. He was also working at a company first, and he sort of tried to convince them to give him part-time working on this. Meanwhile, I had a master student who I had good faith in, but he still impressed me because I said, let's start, right? Yeah, here is some simulated data, and PyTorch is new. Let's try to build a network. And after 3 months, it was running, and it was doing well. And we've been developing this ever since. We call it GraphNet. And the idea is there are more telescopes and things that are similar. We want to try to build a software package that makes it easy for all of these to go in. So the way we do it is we have also workshops, but every experiment who comes, bring a Monte Carlo file and will and contribute to the code by making something that reads this into the framework. And once you're there, the infrastructure is there, right? The different laws, different optimizations, and so on. Different models you control. So this was my still friend Andreas, who lives on the island. Rasmus is the one who could continue. The others also contributed, but they went on to do other things. And Philip is the one who wrote the 8-dimensional likelihood. He's a super person because he's not defending his work. He's like, yeah, let's do this together. I think it's a better idea. And so you look up at the sky, and what I think is also fantastic is that IceCube is starting to see structure in the universe. The Milky Way plane is now at 4.2 sigma, and the nearest active galactic nuclei, they are also getting to 4 sigma. And if you want to hear my blatant dream, it is that, and what limits this is the ability to select with high efficiency the neutrinos and the ability to point. And a little bit the energy, because you have many more neutrinos at low energy that comes from protons hitting the atmosphere and making a local shower. So these are the things, you need all of these things, and I mean, GraphNet just drives them. And if we manage to be, but for the pointing right now, the likelihood is really good. We have a hard time, high energy pointing where you go all the way through the detector is so far, we haven't beaten that. But we want to do it. And we want to improve the selection, and we want to get better energy reconstruction. And instead of sitting waiting for years to get enough statistics, we want to push it beyond the 5 sigma. And Francis Halton, the only theorist I know who conceived and pushed the detector and is still the father of IceCube. He's 82 now. Hang on, Francis, because if you stick around long enough, this could be the Nobel Prize. So we really want him to hang on. So that's why we're working really hard, not to get the Nobel Prize, but to trigger him, part of that. Yeah. Now I want to talk about how we do a graph neural network. And I hope that in 5 minutes it will make sense how you deal with the fact that things are sitting in random places, and how you deal with the fact that there is not a fixed number of inputs that a boosted decision tree normal neural network would insist on. And so here we have a neutrino that hits, and I imagine, very simplified case, there are 7 detector paths that line up, and they have X, Y, Z, and T. They get 28 numbers. Yeah, I really want to spell it out in the numbers and follow where they go. And we want to get to here, the reconstructed neutrino, where we get the energy and the direction and the vertex and the time and so on. Let's go there. The first step is to build the graph. What is a graph? A graph consists of nodes that contain vectors of information, but at least they're the same size. They don't have to be here. Same size. The great thing is you can do different sizes in graph. So when we operate in different detector types, and then you have to connect them with edges. So nodes and edges. And in this case, we just connected them in this simple case. I connected them to the 2 nearest neighbors and Euclidean distance nearest. And because A is closer to B, B is not closer to A necessarily. but they each have two neighbors. And here's already part of the answer to how do you break this problem that you have an unknown number. Here it's 7,000. So once you have that, you put it in vectors, in numbers, and here comes what I call the first miracle. You do a convolution. And in the same way as you in a CNN has, a 3x3 matrix, for example, learnable parameters that you multiply on and get one number out and you put over, you do the same to a node. You say, in my mind, I'm making a copy of this to a new graph. And what goes into node number one? Well, the information that is inputted is the information from node number one and its neighbors. And that's a fixed number. So this means that I can do it with a neural network. I put in the node itself, and I put in the difference to its neighbors. And then, just like the different filters in a CNN that you all add together, you add it all together. And this thing about attention, wouldn't it be nice if we knew what weight to put in front of each of these in order to do it optimally? You can imagine, right? Some of these are better than others. And it's a neural network type, which means that even if you put in, here it's 12 numbers, right? 4.4, you can get something out which is dimensional 32. So that's what you get. You can choose the dimension yourself. And why do you go to a higher dimension? Well, you'll see in a moment that it's good to distribute the information this way, because at some point, you're going to take away the information this way, right? There's 7 of these so far, but it could be 7,000, and we need to get rid of this at some point. And then you continue, you can do this convolution again and again. And we do, and then you might say, okay, how do you know, why do you connect it to those that are just the closest? And what do you do in the next step? Well, the next step, you have 32 latent numbers. But the great thing is, we do it on the first 3, the Euclidean distance of the first 3 in the vector. In the next step, the neural network can learn where to place these and give it new X, Y, Z, and who to connect it with. And we played for a long time, should we do the Minkowski? Should it be Minkowski of ice with index of refraction, or should it be speed of light? Should it be something third? And we tried all, and it didn't matter. Because in the next step, it knew itself, it could learn who to connect with, and this works the best.
So you say that, like in the CNN, when you do next reduction, this is equivalent to this in here, but in the step we use the same network.
The edge convolution here that I showed before, it's the same one for all. But in the next convolution from here to another, it's of course a new one. And the thing is, if you have 2 different types of nodes, you just have 3 edge convolutions. One with 1, one with 2, and 2 with 2. To the same dimension here, and then it finds out. And then you take both the original data and these, so 4 numbers and 32 numbers, and put it into a vector of 36. It's a classic thing you do after this, and then you actually put it through a shallow network to give it more degrees of freedom. Same one for all, so there might be 36 new numbers. But you still have the problem that it's 7 or 7,000. And now you get brutal. You simply say, in the first row, what is the sum of them? What's the mean of them? What's the maximum? And what's the minimum? And that creates 4 vectors, no matter if this is 7 or 7,000. And this is why you want to stretch out the information on this length so that when you hammer it together, you don't lose too much. But now this is fixed size, and then the last neural network puts it in. And of course, this is all one big training thing. And I thought, this is brutal. Shouldn't we take the standard deviation, for example? That was a second level something. And I even bet against my students that it would improve things, and it proved 0. And then we took away everything except max, and then it lost 5%. Okay, it's really good at getting information across here in a way that contains. Yeah, you live and learn. So we do more input features, more neighbors, larger length vectors, more convolutions, different things. I was showing a simple example, but it's complete in its parts. And so here's a drawing of it, how we take and convolute, put all of these together with the original information, and then we take these and have a picture. So, and well, then we started classifying particles. Is it noise or is it a particle? And an IceCube particles are 99.9999% muons and very few neutrinos. IceCube actually reads out the detector more often and records than Atlas. 2,500 hertz. And it's every 6 minutes that there's a neutrino. So it's even more rare than a Higgs. And we found out that this actually doesn't work very well because you want to make multi-classification. You want to give it the option of a neutrino and a muon and noise, because noise actually looks more like neutrinos than muons. And so with only 2 options, it sometimes put things together. But then it works really well. I'm not going to run through this. It does better. You can see here, above here is better, and we typically do this in energy and direction, and we generally do better. At high energy we don't, but that's because the sample we trained on here was low energy, and so just ran out of statistics there. This is compared to the 8-dimensional light.
How long does this take to run?
Yeah, I'll get to that in a moment. And also robustness, I mean systematics, we tested it for systematics, it was as robust. Nothing bad. And we could even take simulated neutrinos, noise, and muons in the right ratios, and then we could plot the data on top and get something which I was highly impressed with. The data from the Carlo was so good. So once we selected neutrinos with green and said which are muon neutrinos and which are that you should track and which are not, then I mean it really is really fantastic. So on all these parameters it did better. Speed. For the oscillation measurement, you have to do a lot of systematic samples. So total, they wanted to reconstruct 140 million events. If you do that with the, we call this the NOMA argument, after the restaurant called NOMA, because it takes 2.5 months on 1,000 CPUs to reconstruct this. We had one single GPU, and you can launch the job on that, and then you can go to NOMA for dinner, and you can bring a friend or a colleague, and you can go for the full menu and wine and have a fantastic evening. When you get sober again, it will be done, and you will have saved money by going to NOMA. I mean, the electricity bill for this is about, what is that, $1,500 or something like that. Whereas it was about $2 or something, for the GPU. It was nothing and took 7 hours. So it's, and the cool thing is, it's faster than 2,500 hertz, which means I dream, of course, this is hard, but I dream about putting one on the South Pole, and cooling is not a problem, and it runs. So, but it's probably not going to happen. It actually uses a lot of power, and the South Pole power is super issue, because the way they still get power in is that all the Hercules planes that they fly in, they fill up completely, then they land, they don't shut off the engine, because they might freeze, and then they defuel them as much as they dare before they fly back. brutal operation. So, and also satellites have become so good that with simple cuts they get it down to 700 hertz, and they can send that north. So it doesn't pay anymore. It used to be that every spring, or when they could get there, there would be hard disks that they would continue. We also did a cackle competition with this, and here we learned. Remember, I said in this edge convolution that it would be nice to have a weight there. This is called a transformer. This is called self-attention. There are beautiful papers on how to do that. And in the cackle, never mind this. I just want to, well, here's our improvement in pointing. Improved over time. And here's the ranking. And 8 out of 10 of the top 10, they said, "You built a beautiful graph. We put a transformer behind." And now we won against you. I mean, you just got the answer of what the solution was straight up. So this was really an experience in seeing how those. Yeah, we came in 14th out of 900 something. So, and we decided not to use the graph. We used something else. So. Yeah. And so in the end, I just want to dream with you in the sense of IceCube has an upgrade plan for generation 2, and a part of the generation 2 collaboration to take the current and just say for high energy, it's not volume. They are so high energy that if you have a PEV, what I didn't think about is if you have a PEV, then even if only 5% gets eventually transferred into muons, then you still get something like 10 TeV muons, right? In the same event going through. It lines up like a Christmas tree. So just drill a lot of holes, same number, out here and put detector. And the reason why it's not in the middle is because this is the quiet sector for other things. And also put in even thinner more, so you can go down in energy and do oscillations much better. And this is going in next winter. So that's going to be cool. And with this, you can really start seeing the universe. And you can do alerts because you're seeing the neutrinos of the universe. You see those patterns. This is from the Blazer neutrino of 270 TeV that came from these violent processes out in the universe, some of which we're blind to in light, and we actually don't know. Tidal disruptions are one of the things when stars get swallowed by large black holes, as they do regularly. Simply the ripping apart in the end is so wild that a nuclear chain reaction is started, and you get these amazing things out. But it doesn't necessarily send out light that you can see, because photons at high energy, they shower in and they're much harder to see, and they also get stopped or diffracted by other things. Protons or anything, you have a hard time pointing with because hey, there's a magnetic field in the universe. So you can't see optics like that. Neutrinos, well, they also have challenges because they don't interact that much. But these energy, they actually do interact so much. Highest energy above, well, towards 1 PeV, the Earth is suddenly not transparent anymore. But you get a lot on the sides. This is where you get the majority of the phase. And with that, you can observe the universe in real time using graph neural networks and that magic convolution operator which bites into the regular data that is irregularly sized. And yeah, that's what I'm also playing with now. Thank you very much.
I have plenty of questions, but I let other people ask first. Yeah, I will start with my plenty of questions. From the end to the beginning. So when you this thing about the graph neural networks on the unfixed input size, this is amazing. here. What I didn't get is that, so how, so the starting of here is already an unfixed number of iterations, right? So I didn't get how in this process, right? You have this graph. You said that sometimes the input is not this amount of points. You may have another graph with more. Yeah. Right. So you just loop over everyone, and then on each step you make one of these with the name.
Yeah.
Okay.
Just loop overall. But even if there are 10,000, we choose that you only connect to 8 years. Right? So this becomes a fixed input.
Right. Yes, that's correct. This is fixed. But
the length of the loop can be different.
Okay.
But it's the same for every step, right? Which means you're just training this local neural network what to do the local bunch of nodes.
I see.
So it doesn't matter the length. You know.
The original length. Yeah. The length that matters when you train is fixed because it's in this.
Yes. And actually, this is what I thought in Piaget, right? In Piaget, it's also hexagonal, right?
Right.
Some and different detector types, right? And sometimes you get a little, and sometimes you get a lot. And I just thought,
wait a second.
doesn't it fit? And you have simulation, I presume. Okay. Okay. Anyway, I might send a link to GraphNet. Just it's not for any other reason as a curiosity to see if this would be fitting for the purpose. But I was surprised how well graphs worked in this case. There were also people who did neural networks where they said, we'll boil whatever this number is down to 15 numbers. Right, and then go on. But that was summary variables and they lost a lot of information in the process. So, but at least it was fast.
Then I had a question about maybe Atlas specific. When you said we decided to drop the cell information, I think, I mean, you still have them always in the ESDs, right?
Yeah.
And then, so, okay, it might make the processing of the data more challenging because we'll need to open those, which are bigger files and stuff.
Yeah, but this was better enough, at least for the round figure processing after data taking. If we can develop it and make it stable enough to work by then, like we have 2 years before the processing started. This would be a very good candidate to plan.
No, but
I will be reprocessing the raw files, so you have this all stuff.
No, right. What I mean that we are not losing this. We are dropping the cells, most of the ALDs in principle.
Yeah.
But we will still have them on it.
No, but they do exist. But suddenly, the ease at which we could put them in
that
got broken. And what I dream about is, I mean, it's not like the energy of electron and photon is taking up a lot of space in the ALD. Meaning, you could have one which is the current method, and then this.
Right.
And then
I see.
And I know that the CP groups don't like having two, and I must admit, I always found E gamma the most conservative group I have ever experienced.
Welcome to gamma,
and it's fun. It's a lot of my phone because I did like 16 France. There's a lot of French people and I've haggled and so on. And I think it's also driven by that a lot of them work on the W mass. And so the goal they see is that this should work for the W mass because then it works for all. But in the case of H2Z gamma, it's the opposite. We don't care about systematic, right? If you can add more data, we'll gladly take double all systematics.
Do you know how approximately, do you know how much size it will take to store the cells for the already reconstructed coding and everything candidates?
I don't know. That's a good question. But this huge campaign of the EDM, the new EDM and stuff and everything, trying to save space. There's a lot of discussions on many areas. So even if it's not maybe dramatic, it was, I can imagine it was a huge fight, but it's not negligible, right? I mean, just for lectures and photos, maybe it's just 2 cells, but then you have the full event with everything. I mean, just will have a lot of cells. I think it's
event, but maybe just something like what was planned to be done in the global, like store all the cells that have a certain number of sigmas and a couple cells around them. And or at least, I mean, we could run this during the
I want to say you only do it for photons above 10 GeV that pass PID loops.
okay, that's it.
You know, something, a filter like that type, same for electrons, right? You don't have a million of them.
Well, that would say a lot.
That would say, you know, then it's only to a small fraction, and those you're interested in, right?
Right. Yes.
So I know there's quite a lot of work in including lower level variables, low level information in the algorithms. For example, the F-tag is testing including the pixel and SCT hits on the actual inference. And the issue is that they can't run it now because the F algorithms run on during the derivation, same as the new tau algorithms. And we are also discussing the same for taus, and that's why we are kind of like all in a 2-year sprint to get this ready before the reprocessing, because at least that's why I mentioned storing the cells in the already reconstructed objects, because for at least for 1,000 for F-tag, I know that's the discussion that is happening right now.
Yeah.
We know that we're going to increase the size, but if we are a bit clever with how we pre-select the number of cells or hits that we end up storing to be able to then rerun inference algorithms with derivations, then we can work with this.
Yeah. And I think this maybe it's too detailed, and I was to gamma combiner when we were having this similar discussions towards the future for tree variables. I know there was a huge non-trivial discussion on why and what to store and why not. But of course, in Atlas, if there's a good reason and there's very support for doing something, even at the price of losing some kilobytes, it might work.
And to me, this is the main reason.
Oh,
The fact that it scales better with power is one of those.
Well, actually, and what you say, I mean, if we manage to somehow convince gamma city or something that it's worth doing it, maybe we don't need to save the cells, do this at reconstruction and hide in the result.
Exactly.
You don't save the cells except for the expression AOD we do now. You run this on the standard reconstruction, standard gamma reconstruction. But this alternative, when you have store the that's a good idea.
Yeah.
But anyway,
that's what I dreamt about for actually the first reconstruction, but then people I was working on something else and they got a lot of administration and all of these things that always happen. So no, but
it's promising.
It was cool that we could measure. To me, the fact that you can measure so directly in the data and see the number, and you can see that it's
this is
so.
One more question.
Sorry, I briefly want to come back to the data and developments. So what's the ratio of events that you
Good question. Frankly, we walked into this and with my student and I, we just took 2 million each and ran it. But we never tried, normally we put lambda here that we can sort of crank up and down, and we never tried to optimize it with that. So there might be better than 18%. But for now, and 2 million is not.
No, it's
not. This is a reasonable amount.
It's a reasonable amount, but it can be done more, right? If you want to do it for Atlas.
I'm actually thinking the other way around. For example, I work on taus, and we don't have enough statistics on taus to do this with data, and then be able to measure completely independent scale factors. Like we cannot take a fraction. Let's say it this way: it will be hard to convince people to spare a fraction of the data that would otherwise be used to measure scale factors to be used in a training for an algorithm like this. Because I see that they would only we will use the same data for both things.
But if you take z to tau, is that not okay to spend?
Yeah, but then you don't have it for the scale factor measurements.
Yeah, but let's say train on half and do scale factors with the other half.
We won't have enough statistics for the scale factor measurements.
How many do you have?
It's very small.
It's one much better than us. I mean, gamma is
I know.
It's pretty much. That's why we can rely on this, let's say, non-standard techniques on gamma because we can do data-driven very good.
For example, for the tau trigger, without critical factor measurements, we cannot, like, during 2024, we changed the L1 configuration 3 times, and we just will do 3 different scale factor for each set of periods, and we don't have statistics. We can only do an entire EL scale factor and just hope that things are going to get absorbed in the scale factor and just have the system if we need to. That's a scenario that we have to do, for example, in Tau. That's why I was just using statistics. We have to use too much statistics, too much data statistics, and maybe a limiting factor for some of the.
I was always of the opinion that Atlas should have put out a lot more data in Monte Carlo publicly, because it would have been, if we had a page from the first Kaggle in 2014 with size 100 million data sizes of complex data where we knew the label answer and so on, then I think that page might have gotten more sites than this page.
Oh, really?
I suspect it would have, but people were so much against it. Now we have 250 million Z2EE in both data Monte Carlo, same for new ones. Put them out. Who has a billion labeled things, right? And if we, a big problem for us is data Monte Carlo protocols. Why don't people outside work a lot on this domain adaptation? Well, that's because they don't have good samples for it. We could be the ones providing, and they would say, that's fun, make a solution for it.
I think it's a matter of personal power, maybe, because we find the public data stuff. So
yes.
Data that is 5 years older, they should be already public.
No, but it's also about creating it, because the public Atlas data, I've looked at it a little bit. I was at a postdoc. It's just a time before you can run anything. Right? If you published, here is a piece of Python code, a data loader that will take this file, load it in fast, and we provide 100,000 files. Right? But that's not what the Atlas data contains. Right? You have to make it specific for a problem that others who don't know particle physics.
Yes. Or give them the way to build. Anyway, we can. I think maybe we can close here. Thanks a lot. Thank you for having me. It's a pleasure. I went perfectly on time. Thank you. No problem. And then.
All right. Cool.
Thank you. Nice. Great.
Now, remember to take this up. I want to take this down.
I think it was given. It was given to me. Yeah, it was given to me.
It's interesting to hear that. I don't think the words are it's fun.